Okay, good evening everyone and welcome to Futures webinar series by BH Futures Foundation. I am Ivana Jeftovic, webinar coordinator. Tonight we will hear about artificial intelligence. The development of artificial general intelligence is going to require algorithms that can do things like inductive reasoning, planning and optimal learning from limited amounts of data. Several efforts are underway to develop these technologies for deployment in future systems. We are currently witnessing these new approaches being given more and more attention as we enter the new and perhaps golden age of artificial general intelligence. In this talk, we will present some of the newer, more general approaches to solving intelligence that are really currently under development with the view to deployment in the intelligence system of the future. Tonight's speaker is our guest, Peter Morgan. Peter is author of the popular report, Machine Learning is Changing the Rules, Ways Businesses Can Utilize Artificial Intelligence to Innovate, published by O'Reilly. He's passionate about artificial intelligence and the positive changes in this technology can and is bringing to society. Peter founded the artificial intelligence consulting company, Deep Learning Partnership, to carry out his mission of helping to bring artificial intelligence to the world. He advises and mentors technology startups and is a speaker at artificial intelligence conferences and meetups. Peter founded the popular London Deep Learning Lab meetup. Links for the mentioned companies are listed down below so you can check it out. Peter, it's an honor to have you here tonight and thank you so much for being with us.
Thanks, Ivana. Okay, so let's get started. So Ivana's just introduced me, and there is a data science conference on the 2nd of July, Croatia, that I'll just put a little shout out now for. So if you want to look out for that, tune in for that as well. Okay, so there's a little book I wrote that Ivana mentioned on a practical book on implementing machine learning in real deployments for companies. That's what I do for a living. I'm a consultant, machine learning consultant. Today's talk's going to be a little more futuristic in that there are no actual deployments yet, and but it's a look towards the future, where we are now, where we want to get to, and how we will get there. So here's an outline of my talk. What is intelligence? Let's start off with the basic question we're trying to solve, and then look at how the world produces intelligent systems, either biological or non-biological. We're trying the non-biological route here. We are the biological. Humans are, the most intelligent thing that we know of in the universe so far, although at times it doesn't seem like it, right? And I'll do a very quick recap of deep learning, and just to see, if that's part of the journey or not, if it's a dead end, or if that's, a step along the way to artificial general intelligence. And hopefully everybody's, at that kind of level. You've heard of deep learning, machine learning. That will probably help understand the talk. But even if you don't, it doesn't really matter. This is a fairly general talk, high level. And then we'll look at AGI, or artificial general intelligence, and we'll see, maybe how we might build such a system, or if it's possible, and then if it is, how we might build it. Then we'll wrap up. So my talk will be about 40 minutes long, and so let's get into it. So, why do we even want to build general intelligence? Well, the idea is, and you may have heard DeepMind say that. It's a company based here in London, under the Google umbrella these days, because then we'll build intelligence and use it to solve everything else, right? That's the big goal. That's the vision. So at the moment, like I say, we're the most intelligent things around. So we're solving, all scientific problems, medicine, climate change, just every problem right now. Humans are tackling it as we have been doing, from the beginning of time. So it's a big vision, right? Is to build systems that can basically supersede us and accelerate science. Isn't that an amazing goal, right? Isn't that an amazing achievement if we could do that? clearly, it's worth a lot of money. So everyone's working on it. Microsoft, Google, a bunch of startups. So let's see where we are on that journey. Okay, now first thing I'll mention is that people do get a little bit worried. Oh my God, what happens when we're no longer the most intelligent things? That's a rather philosophical question, and there's a lot of debate and books being written about that. It's a very hot topic at the moment. It comes under the umbrella of AI safety, and so if you want to look into that, I encourage you to do that. But we'll focus on the engineering in this talk and the science. Okay, we'll leave the philosophical problems to the philosophers, I'm afraid. Or that's a topic for another talk, which I could give too, but I won't on this one. So again, what is intelligence? Is it, beating Go? Is it, winning at StarCraft, beating the best the best players in all of these games, basically, Go, StarCraft, chess, Jeopardy? Well, as amazing achievements as all of those were, like breathtaking, when it happened at the moment, I remember, watching all of them actually, and just, took my breath away. But no, it's not actually general intelligence. Those are examples of very narrow intelligence, impressive as they may be, because the clever system that beat Gary Kasparov at chess, it can't, beat Lee Sedol at Go. It's essentially dumb outside of its very narrow domain in which it's superhuman intelligence. Okay, so they're not generally intelligent machine systems. Okay, so they're all examples of narrow AI. So what is intelligence? Well, Howard Gardner at Harvard a couple of decades ago, it seems so obvious now, but at the time, no one had kind of thought about this or written it down, which it's one of those things. But he did, and I like it because it sort of says there's about 9 different components to intelligence, right? So the Go, the chess, that's the logical mathematical component. That's superhuman at the moment. I mean, a calculator that we can buy for $5 or whatever, can do long multiplication, far faster than we can, okay? So they're clearly superhuman in that domain. But what about the others? Musical, nature, spatial, robots maneuvering, navigating through space-time, self-driving cars, that kind of thing. Intrapersonal. Now, these are the harder ones, aren't they? The personal intelligence, social intelligence, intra, knowing ourselves, and then inter, knowing about others. Okay, so those are probably, the most challenging thing, and the ones that, people say, there are a lot of skeptics, we'll never have, be able to build systems like that. Well, I'm going to argue there's nothing in physics, the laws of physics, that says we can't, and clearly, biology has done it, right? So we're a physical system. There are people, and it's fine. 80% of the world believes in some religion. That's fine too. But I would argue that once you get the right physical systems, that they will be capable, have the capacity of believing in higher powers and stuff like that too. So there's all these philosophical questions come up as well. But they can be, I will try to reduce them to scientific questions, engineering questions. There's linguistic, language, natural language processing, translation, Siri, Google Translate, these are amazing systems, but they're not quite there yet, are they? They're not quite superhuman. Go is, calculators are, but, all of these other types of intelligence we are working on. Okay, we're not there yet. We're not human level intelligence, but we're certainly working on them. The bodily kinesthetic, you watch, is it Atlas, the Boston Robotics, Boston Dynamics, whatever they're called, company, doing flips now, like a gymnast. So we're making a lot of progress on many of on all of them actually. And existential, why are we here? You can imagine a robot sitting there going, why am I here? That's how we'll know we've got general intelligence, probably. And there's a nice, beautiful picture of one right there. And so how far have we come? Well, I've covered all these, we've got the calculation, but they're not creative. We have to tell them what to do. These systems, they're not self-aware. They don't have subjective experience. So the existential down the bottom is 0. They don't ponder, as far as I know, my laptop's not wondering, why it's here. Maybe it is, and just not telling me, but I don't think so. Okay, so how will we get to AGI then? Well, it will take a village to create, it takes a village to create a child. The well-known saying in psychology, well, the same thing, it's going to take a village to create artificial general intelligence. And that village will basically comprise of computer scientists, physicists, neuroscientists, of course, because we are the example, and psychologists, sociologists. So general intelligence is general, right? We're trying to, basically build human level intelligence and then surpass it. So it's going to take not just computer scientists sat inside of Google anymore. It's going to take physicists and neuroscientists and psychologists. No doubt, Microsoft, Google, they have teams like this in place. Okay, so it's a little early. They don't talk about it, but yeah, but people are working on this stuff right now. So and we'll have a look at some of the efforts and some of the history and some of the future of that, which is what this talk's about. Okay, so physical systems, what have we got? So we've got biological, I can argue that plants, bacteria, insects, mammals, us, we're all, nature is full of, intelligent systems. How many species are there? Absolutely millions. And, a locust is intelligent. It's adapted to its environment. It can overcome and reproduce. It doesn't really make goals and accomplish them, though. It doesn't consciously do that. Mammals are the only things that do that. And so there are various levels of intelligence, too. So we're trying to build the human level intelligence, the mammalian intelligence. Perhaps we'll start off with an ape intelligence and then, progress to human level and then superhuman. So that's where we are. So physically, what do we have? We have CPUs, processors, we have GPUs, FPGA, ASICs, and we also, those are all examples of digital processing systems, okay? Those of you who have done a computer science degree or electrical engineering degree, you'll be familiar with all of those. And then we have something called neuromorphic, which processes based on biology, okay? And those are very interesting. Those exist today, and they're quite large as well. We're up to about 1 billion neurons, okay, artificial neurons, and that's like a mouse. We could argue we have mouse level intelligence today, and we'll see a little bit of that later on. And so that's exciting. Digital is always going to be an emulation. Neuromorphic, it's going to be more of a direct simulation. Okay, so there's a difference between an emulation, which is something that you run on a digital processor, and an emulation, which is an actual physical, or simulation rather, which is an actual simulation of the actual physical system, which is the brain. So neuromorphic, we can do simulations. We can run it on real time, just like the brain or artificial neurons. All the rest are emulations on digital processors, which actually takes a lot more energy and time. It's not, we can get there, but it's just, it's not a direct way of getting there, whereas neuromorphic is. And then we have quantum. Is quantum processors, we've all heard of quantum computing nowadays, it's catching the news. Is that a part of the journey or not? We don't know. Maybe the brain uses quantum physics at the level of microtubules. Roger Penrose would argue it does. Who's to argue with him? He's a very clever physicist up there in Oxford. But the fact is, we don't know. Okay, so we'll look a little bit deeper into all of those, and then we'll wrap up at the end, and I'll tell you where we are today. So biology, here's what I mentioned, from the lowest little, single-celled amoeba to the, C. elegans, that little worm there with 137 neurons. We can count them. We built that system actually, so we built that little guy there. A bee we haven't built, that's got about 1 million neurons in that tiny little brain there. It's got a little nervous system, central nervous system, and then the human brain, that's 100 billion neurons. So, that's clearly a tough one to crack. That's what we're trying to go. So a little bit of the big picture, the brain is a system. What level do we attack this on? Do we attack it at the level of atoms and molecules, like, Roger Penrose is doing. That's where the quantum physics is, after all. Or do we start at synapses? Or do we start, at a collection of neurons and synapses, like the connectome? Is that a better level to start? Or do we have to start right down at the molecular level? So these are very fundamental questions that need to be sort of asked and experimented with and probed. This is a science, so, there's theory, but there's also experiment. We test our ideas out. Okay, so if we did start at the neuron, this is what we'd have to build. Now, that's a very complex system, right? But this is quite wonderful because this is how nature does intelligence. Like, who would have guessed, right? We needed such a complex thing to come up with conscious creatures, like ourselves. I mean, this is the very fundamental unit. It's a neuron of intelligence, one could argue. Now, do we have to actually recreate that, or can we do it some other way? Okay, that's a very good question. Clearly, if we could just reproduce, we would just be recreating nature, right? So a lot of this is these artificial neurons are not this complex. The simplified versions. Can they, can that give rise to consciousness? Yeah, we don't know yet. Okay, so clearly it's a tough problem. So it'd be a tough engineering problem to build something like that. Okay, so the next level up really is, we have about 2 million cortical columns made up of these neurons in the brain. There's 100 billion neurons, so you do the math and you see, there's 10,000 neurons per cortical column or something like that, maybe 50,000. So, but there's basically 2 million of these. Maybe these are the fundamental units. Maybe this is, if we build 2 million of these, this is all we'd need to do to build consciousness and human level intelligence. So, I mean, neuroscience as a science has been around 100, 150 years. I mean, a lot of progress has been made in understanding the brain, right, with the hippocampus, all those different parts. And so, we know a heck of a lot actually about intelligence, biological intelligence. So, the question we've got to ask ourselves is, what level do we start at? What level is needed? And then how do we build? A lot of this comes down to an engineering problem. So there's the connectome, there's the next level up. So we started with neuron, the next level up, these cortical columns, then the slightly higher level, I mentioned earlier, the connectome. And so that's, from one side of the brain to the other, our emotions, creativity, poetry, painting, sculpture, engineering structures. Is this the level it's kind of happening at, or does it happen at the cortical column or the neuron, or can we just start here, the kind of bigger conceptual? So these are good questions. These are all good engineering questions. And then of course, if we want to embody this stuff, not just have it running in our laptop or a data center, we need to, we'll need a central nervous system, basically. So if we're going to build robots like Atlas, we're going to have to connect, the CPU, but it also reaches out in a very complex central nervous system as well. The beautiful thing, nature, the Earth's been here 4.5 billion years. First life was about 1 billion years ago, that single cell protozoa. So we've had about 1 billion years to develop this, evolution, dead ends, branching. 99% of species are extinct. So, evolution just tries everything, okay? The laws of physics will try everything. Intelligent, survival of the fittest, the things that are well adapted to the environment, they get to survive. And, over time, what was it, 1 million years ago, the Neanderthal, and then they developed a bigger neocortex, which enabled them to think a bit better than the next type of ape. And all the rest kind of basically went extinct, right? So we won, Homo sapiens, and we're doing, trying to build ourselves, okay, replicate nature. So, and then the last level up is social systems. So, if we build a few robots, they got to get on. We have our social systems. We're a lot more peaceful maybe than we used to be. We still have the capacity to go to war, but maybe there's less war. So we want to build these higher level hierarchies, societal structures. Okay. And there's two sides. People say utopia, dystopia, what's it going to be? Are we going to all get along, these super intelligent machines? Are they going to show us how to live in harmony and, you know, solve science and cancer and everything? Or are they going to be like the Terminator and come and just wipe us out because they see us as kind of destructive and kind of stupid in a way? Okay. Good philosophical questions, right? So we're not there yet. So, but one day we will be, and there's people give kind of serious attention. On biological hardware. Okay, so there's the CPUs, GPUs, and something called the IP Intelligent Processing Unit. There's a company called GraphCore, based out of the UK. They've just got 200 million or $500 million funding every day. It seems to go up to build this new type of processor. Basically, it's not really intelligent. It just does matrix multiplication much faster than the GPU. So it's kind of I probably shouldn't know. It's specialized to do deep learning. It's very good at artificial, deep learning calculations. I'm going to argue deep learning won't get us to general intelligence, but they're very good at classifying and drawing graphs, that kind of stuff. They're not intelligent though. They'll never become conscious. But this is just basically showing you the CPU, GPU, IPU, digital processors. And there they are. That's what they look like. They build them, they ship them, they get paid money for them. So maybe some of you didn't know that, where we are with the ASICs. It's kind of a very, they're calling it like the Cambrian explosion in processors. There's 100 different companies building these ASIC processors, but they're all designed to optimize the deep learning calculations. Okay, so we had the CPU there, the Intel, we had the NVIDIA GPU, AMD make them too, but now there's the Google make the TPU, GraphCore make the bottom two are ASICs. They're really good at deep learning, but they're not going to get us to general intelligence. They're narrow, what I would call narrow AI. Okay. But yeah, there's a lot of money going into building these things right now. A lot of these startups are raising a lot of money to build these for the deep learning. So basically we're solving deep learning, okay, which is not general intelligence, but we're well on the way to optimizing the hell out of that. Okay, but it will not get us to general intelligence. So that's what a cloud TPU looks like. So today we can log into these things. They're a little bit more expensive than the GPUs, which we can also log into. So say I want to do a deep learning calculation. I go to Google Cloud, I just say, you go to Amazon, Google, Microsoft Azure, the three main cloud providers. Only Google have the TPU. That's what they look like. That's 100 petaflops, okay? So that's incredible. I mean, the biggest supercomputer in the world is 1,000 petaflops, and they take up more than 10 times the space. These are very powerful things, but they're very domain specific. They're narrow AI. But they're hugely powerful things and super impressive. If you're into hardware, these things, Google hired 10 years ago some guys to the best in the world to build these things for them, and they kept them secret for a while. That's how DeepMind won AlphaGo, by the way. They use these. Okay, so those are TPUs. Again, this is the largest supercomputer, but it's as dumb as a brick. Okay, it can multiply to very large numbers or factor something very quickly in the flash of an eye, but there's no consciousness, there's no creativity, there's nothing. Okay, so these things they're good at number crunching, but that's about it. But they're hugely impressive and they cost a lot of money. They also use a lot of power. This Summit supercomputer by IBM, so it's not just a matter of raw compute, right? This thing uses 13 million watts of power. The brain uses 30 watts. So it's almost a factor of a million more efficient, okay, the brain. And we do a heck of a lot more biology. Is very clever, isn't it? So, just gives me more and more respect for biology when I see things like this. So yeah, there it is. There's the creation. 1 million, or you could say 4.5 billion years of evolution is optimized to us here today. Einstein, Picasso, Van Gogh, Leonardo da Vinci, who's the smartest guy on the planet today? Maybe Ed Witten at Princeton, he's a physicist. we can do a lot, which computers cannot. So how the heck do we do it, right? It's 30 watts. It's this, you know, fits in the skull. It's 1.5 kilos. So what's going on? What are we missing? Okay, so this is where neuromorphic computing comes in. And there's a project called Spinnaker. So this guy called Steve Ferber up in Manchester, he helped build the ARM processor, which is a CPU, and recently sold to SoftBank, I think, for 20 billion or so. Now after that, 20 years ago, he started to build neuromorphic computing. And so Spinnaker is his effort. It's now part of the Human Brain Project. So these things are, my point is that, you know, these things are real. You may not have heard of them, but, you know, they've been going 20 years now. IBM have an effort called True North. So these things are based on, these processes are based on how the brain works, okay? They're not like the Summit. They're not emulation. They're actually a direct simulation of how the brain, so they're basically building artificial neurons in silicon, okay? Artificial neurons in silicon. And we're up to about 1 billion, which is about a mouse, okay, today. 20 years ago, we had one, right? Now we're up to, everything's on a Moore's law. So yeah, we're up to about 1 billion. Maybe we need just to scale it another 100 times and have a human brain. That's quite possible, actually. It's in the Human Brain Project. It has €1 billion funding. So that's moving as fast as it can move, okay? It's a big European project now. So yeah, and it's available today in the cloud. IBM have theirs. Intel also have something called Loihi. It's a Hawaiian word. There are many startups as well. So again, there are, you know, maybe 50 startups, neuromorphic, just Google it, neuromorphic computing. There are bigger efforts. Brain Scales is another human brain project one started in Germany. Spinnaker is the UK one. True North is IBM, and Intel have one. And then there's all the startups as well. Exciting times. We live in exciting times. So, so basically, you know, we have the digital processing, which I showed you, including the ASICs, the TPUs, the graph core. We have neuromorphic, which is biologically inspired computing, and we have quantum computing. Okay, so, you know, 20 years ago, we just really had the digital. Today, we have 3 different types of computing. And so things are going to get interesting. We live in interesting times. The next 20 years are going to be very interesting in terms of computation, because we now have this neuromorphic, which is like biology, and we also have quantum computing. So things are going to get very, very interesting. So that's what it looks like. There's 5 cabinets. We're up to 10 now. And there's Steve Ferber. And this is how it scales. You start off with 1,000 neurons in a core. You put 18 cores on a chip. Then you put 48. This is all engineering at this point. It goes to a fab and it gets built. You have 48 chips on a board, 24 boards in a rack. And then you put 5 racks per cabinet and 10 cabinets. That's the intelligence of a mouse right there. So that's 1 billion artificial neurons, much bigger than a biological neuron. But again, all of this is on Moore's law. When we had 1,000, remember, in 1970, I think, we had 1,024, the first processor that ever built. And it was the size of a 1 inch by 1 inch, 1,000 neurons. Now we can fit 10 billion neurons on a 1 inch by 1 inch. Okay, it's Moore's law. So these things are shrinking, you know, so, you know, it's on a trajectory. So that will scale down nicely in 10, 20 years. That will be the size of a mouse brain. Okay, so that's what they look like. That's on Brain Scales on the left. That's a Human Brain Project from Germany. And then there's Google GPUs on the right. So analog versus digital. I'm arguing that we need the neuromorphic on the left to get us to general intelligence. The one on the right will do it. We can simulate it, but it's like 1,000 times less efficient. As impressive as an engineering feat as that is, but it's very good at deep learning. Okay, what about quantum? Maybe we're making progress there. We're up to about 100 qubits, quantum bits. That's on its own Moore's law. So, you know, within 10 years, we'll be on 1,000, then we'll start doing interesting calculations. And does the brain use quantum? Roger Penrose would argue yes. You know, we don't know if we have to go to that level. Roger Penrose actually argues that consciousness is the only way to get a conscious system is to go down to the quantum level. Interesting, huh? Okay, so there we have it. Those are the 4 types of compute. We have digital, we have neuromorphic, we have quantum, and we have biology. Okay, and that's what they look like at the microscopic level. So in some sense, the computation, the physics of computation is called information processing, okay? And in some sense, when you get down to it, the equations are the same for the 3 classical systems. For the quantum computing, they're different. They obey the laws of quantum mechanics. But theoretically, if you're interested, you could just Google information processing and eventually you'd wind up here. But the trick is to build them, right? Okay, so that's what the data center of the future is going to look like. Right now, that's just almost 99% classical digital computing. There's a few Spinnaker machines. You can buy that Spinnaker processor. You can actually buy them. But not many data centers have them. But the point is, you can buy them. Quantum computing, you can also buy. You can log into the cloud today and log into an IBM machine. They have 20 quantum computers on the cloud as of today, and also log into a Rigetti machine. Amazon and Azure, Microsoft, and their cloud are also going to offer quantum computing as a service soon. You can log into Spinnaker at the Human Brain Project, but I think you have to be an academic to do that. It won't be long before they commercialize that too. But you can see the road ahead. I'm arguing that probably neuromorphic is the way to get us to general intelligence. Quantum is going to be very useful for simulating molecules, molecular dynamics, drug discovery, and classical will be good for the internet, our iPhones, etc. So each type of computing has its own specific use. I'm going to argue neuromorphic is probably the one for AGI. Okay, so deep learning. What about deep learning? Just an eye on the time here. 30 minutes. Okay, probably be another 15 minutes. Okay, probably 2/3 through the talk. So we on this call, everyone's heard of deep learning. I make a living out of it. I've been doing it for 6 years, 7 years now. That's, it's not going to get us to general intelligence. So I basically put that in here to point that out. It's good at classifying images. It does some sort of language translation and text to speech, etc. There's a neural network, deep learning optimized chip in all phones now, all PC, all laptops. Okay, it's called system on a chip. You have your CPU, you have your GPU, but you also have a neural networking deep learning processor as well these days. Okay, so they're used for some things, mostly to do with image recognition, classification, and language. Okay, so it just swaps over to whatever processor is best for the time. So if you have an application on your phone that requires deep learning, it will swap over to the deep learning processor. And these are known as co-processors. So the CPU is always the main core processor, but if it has something that it needs to offload onto the GPU or the deep learning processor, it will do, and then the back and forth between CPU, GPU, they call it co-processors. So, these neural network are on all devices these days, okay? Probably in the last 5 years, they've started putting them in all devices because deep learning is a thing now, right? There's no neuromorphic processors yet. Maybe that's to come. Okay, they're too big, right? They won't fit in the phone yet. You have to use them on the cloud. And so, we've all heard of the different framework. TensorFlow is the most popular. PyTorch has become quite popular as well. The two main deep learning frameworks are TensorFlow and PyTorch, if you're interested. And that's it. This isn't a talk about deep learning or TensorFlow or PyTorch, but I just put it in there to say whether, deep learning is getting all the press, is it part of the journey? No. Doesn't give you what a neuron does. No, it can do, like I say, image classification, language, but it will not do the other types of intelligence. Remember, the creativity, the moving around, navigation through space, interpersonal, won't give you that at all. zilch, zero. Okay, so we're going to need something else. I've mentioned neuromorphic, but what about the theory? Okay, so let's have a quick look at that now. Okay, so general theories of intelligence. So, what do we need? What are the different approaches? I'll cover them. There's one called active inference, which I'm going to really focus on. And then what do we need to build an AGI processor? Okay, so what do we need? So what we do is we turn to physics, right? We're a physical system, a human brain, the brain of a fly, a snake, a monkey. These are all physical systems. And so what do we need to understand in physics? There's no easy way out. There's no magic. We got to go down. We got to do the math, right? So, are we missing anything in physics? Well, there's everything we know about the universe right there. And all of that can be described as there's a very fundamental principle called the principle of least action. Now, about 2 or 3 years ago, there's a book published 2 years ago, in fact, by Cambridge University Press called the principle of least action. All of physics can be actually reframed as, this principle, which basically says, now it gets mathematical for the next couple of slides, switch off if you want to. But conceptually, what we do is we write down something called the action, which we denote as S, and we write down that equation. It basically goes back to Hamilton, Lagrange, about 100, 150 years ago. And, it's quite common if you're a physicist to formulate things in terms of Lagrangians, Hamiltonians. The action is a function of these Lagrangians, and you do some scary math, but basically the point is that I can formulate any system in the world, whether it's a brain or a car going down the road, a couple of billiard balls on a billiard table, anything I like, atomic, quantum physics, classical physics, the universe, cosmology. Turns out there's this very unifying principle called the principle of least action, okay? So maybe we could start there, okay? So what we have to do, what's different about the brain compared to, say, a black hole or a system of galaxies or, a chemical interaction, okay? What's different here? So we got to understand the system we're trying to model, right? So we need to build a system that can model the world. Okay, just like a mouse makes a little model of the maze, or we make a model of how we're going to make money or get up and go to work, or, get in the car and go on a holiday. We're always modeling the world, crossing the road without getting run over, etc., etc. Finding a mate, getting married, having kids. We're modeling all the time. Solving, a problem in chemistry, we're modeling. We're always trying to model the world. So we need to build a system that can do that using the principle of least action. That to me is general. That would be a generally intelligent system. Okay, so how do we go about doing that? Just so happens that a lot of very smart people in the world have been working on this for the last 30 years or so and doing the math. Okay, they've been writing papers, publishing them, writing the equations down, building prototype systems, okay? But these systems have to be able to explain and understand what they see, play all these board games, Go, chess, Sudoku, but also, cross the street without getting run over. They have to be able to model their world, okay? If you build a robot, no use having it just walk in front of a car, right? It has to be modeling its environment. I mean, that Atlas robot doing flips, that's mind-boggling. So that's a robot modeling its world, that it can do that. But also that's physical intelligence. It also has to be smart, right? That Atlas is dumb as a brick, it can't play chess. We have to have the whole thing, like we have, 1.5 kilos, 30 watts. We have to make the whole thing, which is where the neuromorphic process would come in. So it can plan, problem solve, build new models as they learn more about the world, update their prior knowledge, just like we do, imagining things, having imagination, interpersonal skills. Okay, so here's some approaches. I mentioned some very clever people who work on this. There's a guy called Karl Friston here at the UCL in London. There's a guy Tishby in Israel, Bialek at Princeton. Hooter is in Australia at the moment. He started in Germany, I think. Schmidhuber is at IDSTIA in Switzerland. He's set up a company called Gödel Machine with lots of patents. He's a very smart guy. So, and there's many more. So these are very clever people been, trying to solve intelligence for their life. I mean, that, as children, They were going, how do I solve intelligence? Some of us say, well, how do I get up at 9 and come home at 5? I mean, these guys, they're just like Einstein, natural born with this thing, right? I want to solve intelligence. So these are the guys. Okay, so let's focus in on Karl Friston. So basically, he's using the principle of least action. I call it the free energy principle, but it's the same thing, basically. It uses physics. Okay, so basically, his stance is that systems, operate in the world to minimize their free energy, something called the free energy. And, that will cause them to explore. You get the explore, exploit trade-off. They will explore their environment. How else do we learn? Remember, as little kids, watch a baby. They just roam around, crawl around, exploring their environment, putting things in their mouth. This is how we learn. Okay, so the principle of free energy this is what basically our brains are doing. They're just minimizing the free energy the whole time. If there's uncertainty, we want to minimize it, right? Maybe that's what the best definition of intelligence is: minimizing uncertainty as quickly as possible and effectively as possible. Okay, how do we, solve chemistry or physics or figure out the universe? Well, these are uncertainties. We're just trying to minimize them as quickly as possible. And it turns out the brain, we're not separate from the universe. Okay, we're a physical system within the universe, which, our environment. They're interacting the whole time. So it's just physics, okay, basically. I say just in quotation mark. So you can write down equations for these interactions and how a system might minimize its free energy. And here he is. That's Karl Friston. We could listen to him for 2 seconds. So it gets technical quite quickly. A lot to do with probability, Bayesian inference. He mentioned the word inference. So the brain, it's always there's always sensory input, right? Even when we're sleeping, we have dreams. There's subconscious. There's conscious. I mean, there's internal sensory perception. There's perception from our environment. There's mental illness, schizophrenia, where the information processing goes awry. It's a complex system. There's 100 billion neurons, all different parts, layers upon layers through evolution. The neocortex is what enables us to come up with things like the theory of relativity and build cars and, solve physics and chemistry problems and mathematics. It's a complex system, but it's basically a system that's based on the free energy principle, which you heard Professor Friston explaining a little bit there. That's what it looks like in a diagram. These other guys like Schmidt-Huber, they have their own systems, but I think they'll all basically boil down to, the free energy principle. The equations, they look kind of similar. They may use different terminology, vocabulary, but physics is physics, right? Okay, so they're all trying to model this physical system called the brain. Right, so we have external states, internal states, and there's only a few more slides now. And something called Markov blanket, which kind of delineates the two, the internal from the external environment. But there's no real, there's no fixed thing, right? I mean, things enter and we take action, enter our brain, and we take action, right? All the time. We're always interacting with our environment through our pores and our skin. There is no fixed line, but it's a theoretical construct to help us do the maths. Okay, and it's completely general. It works for cells. Cells are intelligent. They reproduce. they survive in their environment, right up to brains. Okay, and here's the math, pretty ugly. Okay, so last few slides. Can we build general intelligence? Okay, very clever math. A lot of these guys might end up getting Nobel Prizes and whatnot, because one could argue it is maybe the defining problem of our time, right? To build intelligence, solve climate change, solve cancer, build intelligence. These are the big problems. If someone solves it and builds a system, they're going to get a lot of money and a lot of prizes. So I mean, a lot of these guys have a super lot of recognition already if you're in the field. So, and it's a combination of, like I showed before, computer science. So a lot of them are computer science, physics, and neuroscience. So a lot of them are neuroscientists. But some are more computer science, but with a little neuroscience. Some are neuroscientists with a little computer science, a little physics. But yeah, the one thing is they're all really, really good at math. Okay, so can we build? The answer is yes. We have candidate theories. We have some algorithm software, some math. We have the hardware now, and we have masses of data sets. So when, right, basically the question is not how, but if, it's when. It's going to be like a TensorFlow for general intelligence, just to kind of touch base with something we're familiar with. And we're going to need a lot of software engineers to actually build these systems, and hardware engineers too, to build the neuromorphic processors. It's a big project. I mean, the Human Brain Project, is an Apollo project of our time. It's going to require funding. There's a lot of funding going into this stuff at the moment. And you got the Human Brain Project, DeepMind. You got the US Brain Project. China's working on this. Everyone's working on it. Should we build AGI? Again, that comes back to the philosophical question, safety, ethics, singularity. But that's for another time. Okay, so here are some AGI projects I mentioned from countries all over the world, all very, very viable projects, in my opinion, all of them. No clear winner. All good stuff. Okay, so in conclusion, it's obvious that deep learning is lacking the foundations to build general intelligence. It's based on statistics, not physics. It's a statistical hack. It's very clever, but it takes 1,000,000 times as much energy as the brain to do, about 1% of what the brain does. So clearly that's a no. Research groups are looking into bioplausible models. That's the way to get there. That's, in terms of theory and hardware. So the real question is when, right? So we've got prototypes now. Schmidt-Huber, he's building stuff, commercializing it. Karl Friston, has a huge code base, hundreds of papers. So we're on our way. We're at the beginning of an exponential curve, I'd say, right? And so yeah, it's not a when. It's not a defining moment. It's a continuum. We're at the beginning. We've got a billion neurons, artificial neurons, in a Human Brain Project. We've got the brain of a mouse that can do Sudoku puzzles, that can solve stuff that humans can solve, that deep learning would never be able to solve, at 1,000 times less energy. So we've got the hardware. That's on its own Moore's law. And what else? So finally, even Geoff Hinton, he's a godfather of deep learning, right? Won a Turing Award with Jan LeCun and Yoshua Bengio last year for deep learning. He's saying, assuming he knows as much about anybody about deep learning, he's one of the founders. Assuming that the computer industry can keep producing better hardware, I think business as usual is going to take us a long way. He's talking about the TPUs, the graph core, all of that. Obviously, if we get big conceptual breakthroughs, probably from neuroscience, it'll take us further. I think one of the big breakthroughs that's going to come is we're going to understand the brain. So yeah, it's all about understanding how nature has done it. And nature is used the laws of physics. And Karl Friston, this active inference, formulates that beautifully in some beautiful mathematics.
Okay, so was this your final word? Can we move on to questions?
Yeah, so any questions?
Yeah.
Thank you.
Okay. Okay, we have a few questions. It was a really enthusiastic speech of yours, and so these are the questions. If we manage to create artificial general intelligence, what would be the odds of the AGI being sentient?
Yeah, so that will fall out naturally. Okay, so sentience is part of intelligence. Remember the types of intelligence? So that's the existential part. That's what that meant. So yeah, they have to be sentient.
Okay.
They have to be sentient. I mean, first of all, we'll build ape-like intelligence. Apes are sentient, right? They know what's going on in that level. Okay, so they will be sentient, and as we get more and more intelligent, they'll become more and more sentient. Yeah.
Okay.
Have you ever seen that movie, Her? When that's a beautiful movie with Joaquin Phoenix. Have you seen it? Her. The thing on the iPhone gets smarter and smarter, more and more sentient until it goes off into its, hyper universe somewhere. I mean, that's the kind of thing. It will start kind of like human level, ape level, then get to human level, but then go into, they'll be more sentient than us.
Okay, and together with this question, if it grasps the concept of the humor, it could troll us by giving us false predictions. Can you trust it and secure it? Is that slavery?
Yeah, so that's a good question too. No, they'll have rights like us, right? Just like, there's animal rights, animal cruelty is a no-no, right? You go to prison if you harm an animal, right? It's not right. So yeah, that comes down to ethics and law. Yeah, they'll have their own rights. They will have rights. You still there?
Okay. And what do you think about artificial intelligence in drug design?
Yeah, so it's going to help a lot. So right now it's a good question because we're using deep learning to help us discover drugs, to explore the chemical molecular dynamic space much quicker than we can if we do it ourselves. Okay, so deep learning is actually accelerating drug discovery right now. Okay, the idea is to accelerate it even further by using an artificially general intelligence system. So yes, right now deep learning is absolutely accelerating drug discovery, as witnessed in the DeepMind winning the protein building competition recently, which is molecular dynamics, which is similar to drug discovery.
Okay. So there's just one comment. A lot of science fiction's work gave rise and inspiration to many great technologies and research. So they want to know which science fiction or any other general books gave you inspiration and helped you shape yourself towards the professional that you are today.
Yeah, so science fiction is, when I was younger, I used to always read science fiction, watch Star Trek, huge science fiction fan, really. So yeah, I mean, Asimov's Foundation series, Robert Heinlein, Isaac Asimov, Arthur C. Clarke, those are kind of the, but yeah, there's new guys around right now with, different science fiction series. Always good for the imagination to read science fiction. There's nothing wrong. In fact, it's encouraged, right? Imagination is a great thing. That's that's the start of all science is imagination. So yeah, and you can encourage it.
Okay. And if we ever reach artificial general intelligence, do you think laws would be implemented on time, or we would firstly see abuse of artificial general intelligence in daily life? You partially gave the answer on this.
Yeah, so there's always going to be good actors and bad actors, right? So yeah, we're going to have to come up with laws and try to find ways of enforcing it. There's going to be some silly things happen, of course, just like with nuclear energy, right? All very powerful technologies can get misused by bad actors. And so, yeah, we're going to have to keep an eye out for that. We have to enforce it. We have to have police at that point, right? Yeah.
Yeah, of course. And the final question, as far as I can see, one more. Okay, how artificial general intelligence could affect religions.
What's that?
Okay, how the artificial general intelligence could affect religions.
Oh yeah, so I did mention that. I think sentient being will have the capacity for religion and religious and spirituality and all that good stuff. So yeah, it comes along with intelligent. It's a type of intelligence. Spiritual intelligence is a type of intelligence.
Yeah, of course. Okay, as far as I can see, that those are all questions, but we will wait a few minutes more. Thank you so much for your answers and for this presentation and being with us tonight. It was really enthusiastic and inspiring to watch this and to understand it a bit more. So we really thank you so much, me and all the people from Foundation. And
Sure. I look forward to watching it on YouTube.
Yeah, and we hope to collaborate again with you, of course. So thank you so much. There are no more questions, so I would call it. And okay, thank you everyone for watching. See you on the next webinar.